Dynamics of rotation. Solid systems around us can have different types of motion. A box can slide on a rectilinear, horizontal, or inclined track. A bicycle wheel or a fan can rotate around a fixed axis. These solids may also remain at rest or in equilibrium under some determined conditions. In this chapter, we are going to study simple rotational motions of some solid systems and the conditions under which such systems remain in equilibrium. Objectives: 1. Distinguish the translational motion from the rotational motion of a rigid system. 2. Define the moment of inertia of a particle with respect to an axis of rotation. 3. Determine the moment of a force with respect to an axis of rotation. 4. Determine the moment of a couple. 5. Apply the conditions of equilibrium of a solid. And finally, apply Newton's second law of a solid rotating around a fixed axis. In the first situation, we are going to study translation. If we observe these three figures, figure 1, 2, and 3. In figure 1, a rocket describes a rectilinear path, while in figure 2, the solid represented by the vector AB describes a circular path, and in figure 3, this solid describes a curvilinear path. So, if we observe the successive positions of the solids, the trajectories are very different. In figure 1, rectilinear, since the trajectory is a straight line. In figure 2, circular, since the trajectory is a circle. And in figure 3 or C, curvilinear, since the trajectory is a curve. However, in each case, the segment AB linked to the solid remains parallel to the same line of action during the motion. For example, in figure 2, the solid is represented by the vector AB. Vector AB conserves its line of action in all positions, so the vector AB remains parallel to itself in all positions in this figure. And in figure C, also the vector AB remains parallel to itself. The line of action of vector AB is parallel. For example, the line of action of vector AB in position 1, A1, B1, is parallel to the line of action of vector A2, B2. And in this figure, the line of action of vector AB is parallel to itself in all positions represented on the figure. So, in these three cases, a translational motion takes place. A solid is in translational motion when every segment connecting any 2 points of this solid maintains a constant line of action, that is, when remains parallel to itself during motion. We therefore notice that all the translations are not necessarily rectilinear and can be rectilinear or straight, as shown in figure 1, since the rocket describes a straight line, or circular, as shown in figure 2, since the solid AB, represented by the vector AB, describes a circular path, or curvilinear, as shown in figure 3, since this solid, represented by the vector AB, each point of the vector AB, A or B, describe a curvilinear path. While in three figures, translation takes place, but the form of trajectory is different. In the first figure, the trajectory is straight or rectilinear. In the second figure, it is circular, and in third figure the trajectory is curvilinear. In figure B, we notice that the point A and the point B have the same circular path with the same radius, but only the center is different. This is the circle described by the point B, and this is the circle described by the point A. If we compare the trajectories of A and B, we find that these trajectories are circular. So A and B describe two circles. The first is relative to B and the second is relative to A. The two trajectories are identical, for example circular in this figure. The circle relative to B is centered at OB, and the circle relative to point A is centered at OA, while OA and OB are different, since the center O relative to the circle B and the center O relative to the circle A are not confound. All the points follow identical trajectories. For example, A and B in this figure follow identical trajectories, that is circle, which are deduced from each other by translation. If we consider the circle described by B and the circle described by A, we can obtain the circle relative to B from the circle relative to A by translation, and the vector of translation used is the vector AB. To obtain the circle relative to B from the circle relative to A, we make a translation using the vector of translation AB starting from the circle relative to A. So, all the points follow identical trajectories which are deduced from each other by translation. The trajectories of the different points of the solid in translation are therefore stackable. In this figure, we consider the solid or this solid. On this solid, we take 2 points, M and P. Knowing that this solid is in translational motion, if we represent the velocity vector at point M and at point P, we find that the velocity vectors are identical at an instant t, for example at instant t1. So, all the points of a solid at each instant, for example at instant t1, all the points have the same velocity vector, or the velocity vectors of all points are identical because this velocity vector have the same line of action, same direction, and same magnitude. So, at any instant t, for example at instant t1, all the points of this solid have the same velocity vector. But between two different instants, for example between instant t1 and instant t2, this point or any point of the solid cannot have, or the velocity vector of this point may be changed. For example, if we consider an accelerated motion, any point of a solid in accelerated motion, its velocity change during the motion. So, if we compare the velocity between two instants in an accelerated motion, we find that, for example, the velocity is varied, since in an accelerated motion the velocity increases. So, for example, for the point M, between the two instants t1 and t2, the velocity vector, for example, relative to point m at instant t1, for example, it has a value equal 8 meters per second, for example. At instant t2, the velocity of the same point m can have another value, since if the motion is accelerated, so the speed or the value of velocity at instant t2 for the point m is greater than its value for the same point at the instant t1, since we talk about an accelerated motion. And if we consider a circular motion, the velocity vectors does not have the same line of action, for example, for the same point. So, during the translational motion, the speed vectors of a same point can be modified between two instants. This modification, for example, takes place in value if we consider an accelerated motion, or in line of action if we consider a circular motion. So, finally, all the points of a solid in translation have at each instant the same velocity vector, and this velocity vector is called v instantaneous or v of t of the solid at this instant t, while during the translational motion the speed vectors of the same or of a same point can be modified in value if we take in consideration an accelerated motion, or in line of action if we take in consideration a circular motion.